Okay, did have a question from one person who used the whole doggone tangent plane to answer a question could have been answered with differentials. Okay, but that's fine. It's good, and if you can understand one, you can understand the other. So here's one of our standard blocks. This represents, say, the XY plane is here in this sum function, and this is an approximation of some section of that function. Or maybe what we've got is actually just a plane, and this is a plane. Top of this thing is a plane, same as the plane that we're talking about in the XYZ space. Okay, function f of xy. Okay, well, function has a value here, has a slope here, has a slope here. Okay, in other words, the slope here is going to be your partial derivative with respect to y at this point, calculated at this xy value. And the slope here will be partial derivative with respect to x, is calculated again at this point. Okay. Now, if we want to figure out how much the function changes between here and here, we just figure out what our change in x, change in y is, and multiply it by that slope. That should be pretty clear. So that's just your partial derivative with respect to y evaluated at this point times your delta y. Okay. If we want to know how much changes between here and here, we multiply this slope by the change in x. Now, if x is this way, your change in x here would be negative, but that's perfectly legitimate. It often happens. Okay, you don't know which way your variables are going to change. Okay, and then we get the change in the value of the function from here to here, and that is the change between this value, that's your f of x, y, say, and this value, which is your f of x plus delta x, y. Okay. Now, if I want to change from here to here, I can add this change to this change. If this is a perfect plane, that's going to give me the exact change from here to here. Now, if this isn't a perfect plane, if I got a little curvature here and a little curvature here, then I also could have curvature here that's different than the curvature here. So extrapolating from this point to this point is going to be a little more fraught with difficulty. Okay. But if the intervals are small, there isn't time for the curvature. There isn't enough space. There's enough distance for the curvature to make that much difference. Okay. So for small delta x and delta y, I can approximate the change from here to here by adding the change from here to here and the change from here to here. That makes sense? That's the differential. Okay. I'll draw it on the board here in a second just to clarify. And I don't need the equation of the tangent plane to do that. So if you use the equation of the tangent plane to answer the question, well, you took an extra 5 minutes. Okay. You got it right, I think. I usually check procedure. I don't always check the numbers. Okay, if they're easy numbers, I'll do them in my head, reconcile it. But I'm not going to take the time to work out the details that I know you can work out. I will always check to see that the numbers make sense. Whether they're totally accurate, that's in your, so do your numbers accurately. Okay. This is going to lead us then kind of directly to the idea of a directional derivative. The directional derivative would be like the derivative in this direction. Now, what's a derivative? It's the rate at which the function changes in whatever direction. So I'm moving in this direction. What's the rate of change of the function? Okay. And then I multiply that by how far it is, and I get an approximation to what the function ought to be here. Does that make sense? Well, it's pretty easy to do that. If you know the rate of change in this direction and the rate of change in this direction, you just do the appropriate rate of change. You combine those in the appropriate way to get the rate of change in whatever direction. Because the rate of change in this direction and the rate of change in this direction determine the instantaneous rate of change in any direction from this point. Okay? And that's called the directional derivative. We'll write out some symbols. So I guess since the topic came up, the section 5 is on chain rule, and we're going to talk about that. But since this has come up, I'm going to talk about directional derivatives because I don't need the chain rule to do that. So I'm just going to say what happens. Okay, this is, I'm not sure I want to do a three-dimensional picture here. I'm going to just do in 2 dimensions. Here's y. Here's some point, and we might call it x naught, y naught, but I'm just going to call it x, y. Okay? The rate of change in the x direction is fx, and the rate of change as you move in the y direction is fy, evaluated at xy. At this specific point, that's your rate of change. Okay. Now, I want the rate of change in some other direction. Okay. Question, what's the rate of change in this direction? Well, I can move from here to a point out here by moving the x direction, then by moving in the y direction. If I know how much the function changes for this movement and how much it changes for this movement, then I know how much it changes from here to here. Okay? And I can divide that change by this distance to get the rate of change. Does that make sense? That's what we mean by the rate of change. The rate of change from here to here might be a little bit different from the rate of change from here to here. But if this is a very small, okay, if this point is very close to this point, then the rate of change in the y direction, or the rate of change in any direction is not going to have much room to change, okay? So I can say that, first of all, the change from here to here should be pretty much the same as the change from here to here. Change from here to here ought to be pretty much the same as the change from here to here. But we're going to base our calculation of the rate of change on the 2 partial derivatives evaluated at this point. Okay, so I'm going to use this displacement and this displacement as a basis for calculating the change between here and here. So I'm going to do a bigger picture of that. Do it up here. Okay, so I'm just going to bring this picture down here with it somewhat bigger. I have a delta X here. And a delta Y here. Change in F is approximately equal to Fx delta X plus Fy delta Y. Now that's the change from this point to this point. Let's call this point A, call this point B. So what I'm saying is delta FAV is approximately equal to this. Delta X and delta Y are both small. Assuming a well-behaved function, a function whose derivatives, higher derivatives, are all continuous and bounded. Okay. Smooth. Okay, well, that's pretty simple to understand, and that's exactly what I was saying on the one homework problem where some people wanted to find the change in a function from point A to point B and found the whole equation of the tangent plane and evaluated the tangent plane at this point. Okay? Equivalent to just calculating how much you change from here to here and how much you change from here to here. Okay? And that's differential versus the whole tangent plane. Then you need to do both because you know the tangent plane. If you're just trying to calculate one point, then you probably want to use differential. If you want a formula for all the points near this thing, as long as the tangent plane is valid, you probably use a tangent plane. Okay, two different pictures for the same situation. Okay. Now, how do we calculate the rate of change from A to B? Actually, if I'm going to use the notation for differentials and changes in functions is, it's always troubled me a little bit, but I can't think of a better way to do it without making it harder to understand. If we're doing differentials, we kind of do a df and a dx and a dy, even though df, dx, and dy generally refer to infinitesimal quantities that approach zero and stuff like that. The whole concept of infinitesimal is a little ambiguous. the delta F would actually stand for the change, the actual change, the function value here minus the function value here. This is an approximation to the change in the function. I think I gave at least one of you a couple of notes on that figure that said, had the picture with the deltas and the ABs and stuff like that. All right. So the rate of change is approximately equal to then to the change in the value of the function over the distance from A to B. Okay. And that is equal to fx cosine theta plus fy sine theta, where triangle theta. Because your dx here, and I guess I should label that as a dx. You got a triangle here. The hypotenuse is the square root of dx squared plus dy squared. The adjacent side is dx, the opposite side is dy. So dx over that square root gives you the cosine of theta, dy over that square root gives you the sine of theta. So you have to agree that that would be the approximate rate at which you change as you move away from this point. Now, the further you get away, the less accurate the approximation. And that's actually called our directional derivative. Now, there's a rigorous definition of the thing. And incidentally, I do have to leave at past today. Doctor appointment, I couldn't get one any later in the day. And didn't really have a good choice on it. So I hate to cut you guys 20 minutes early. Actually, since I usually run over, I'm probably just making up for what I've done. Okay, so there it is. Now there's another way to represent this. Okay, I'm going to say if del F, it's an upside down delta with an arrow over it. That's del F, okay? This is called the gradient. It's a gradient operator. The del operator gives you a gradient. It does other things sometimes too, but and U equals cosine theta I plus sine theta j. then this thing I said is the directional derivative is just equal to the dot product. Fx times cosine of x, Fy times sine theta, Fx times cosine theta, Fy times sine theta. There's our directional derivative. This is definite the directional derivative of f in the direction of u. I note that u is a unit vector. Magnitude is the cosine squared plus the sine squared, which is 1. Okay? Square root thereof is still 1. And we can sometimes denote that f's of u. And there are other ways of denoting it that you'll see in your text. But that's the idea. It's very easy to calculate and very easy to use. So if I've got this function, I want to know how quickly it changes in that direction. Let's say the function is the temperature of a surface. So it is a surface down here, and you could think of the temperature, you could think of a graph that indicates the temperature, but it's not a real thing, but it's a graph that represents it, okay? So all we really need to do is think of temperature in this plane. It's a function of position. And at any given point, we could see the rate at which the temperature changes would go this way or that way or that way or that way. And it turns out that the rate at which temperature is changing at a point, well, the direction of maximum increase of the temperature is the direction of the gradient. Okay, I'll just state that right now because limited time. I'll just say gradient gives the maximum rate of change in the direction in which the maximum rate of change, ROC, standing for rate of change, direction in which it occurs. You could also do this in 3 dimensions. You know, we have a temperature function in this room. Okay, we have air currents and stuff like that. At any given instant, what's the temperature gradient? Well, it feels a little cooler in that direction. The temperature gradient is probably in that direction at that instant. And air circulation changes continuously. So what I said there is no longer true, but that one instant in time, that might have been true. That makes sense? That's also the direction in which heat flows, especially in a solid. If you got a fluid like air, heat isn't just flowing, it's also being carried around by convection, and it gets really complicated. Physics of it and the engineering, I think, can get really, really complex. Just for a flat metal plate that's maybe somewhat insulated, they're insulated or not, you don't have material flowing around, but you do have temperature changes. So, that's very interesting stuff. Okay. The other thing then is, okay, so let's say here is a point, and here's gradient. So here's a point, X and Y. The gradient, which is real easy to calculate, you do the partial derivatives. Put them in front of the I, J, and K vectors. Okay. Direction of maximum increase. So perpendicular to that is the direction of which the function is unchanging. If we have a level curve, where f of x, y is constant, then the gradients are perpendicular to level curve. If f of x, y, z is constant, that's a level surface. And the gradients are, again, perpendicular to the level surface. So that the gradients give you normal vectors. Gradient to a level surface is a normal vector. Okay, these are important ideas, important images. Does halfway make sense? Those are the ideas that you really end up using. There are more. I mean, there's more subtle stuff. This is an introduction. And I'm not going to be able to hit every point, partly because of limited time. And also, I'm not assigning this per se, because spring break's coming up. And the thing I want you to be sure you do, if you're not already pretty well conversant with the stuff we've done so far, so I do want you to come back. I mean, theoretically, you should right now have pretty good mastery over everything we've done. But not too long after we get back, we're gonna have a midterm test. So if you do have time over spring break, don't ruin your life to doing it. Unless you'd rather ruin your life that way than by not doing well in this course. Uh, and try to get everything nailed down pretty well as if you're going to have a test, because we're going to cover the rest of this chapter. Then we're going to have a big old midterm test. Okay. And that's got to be by the end of the month. We got to have that done by the drop date. I really hope nobody drops. I don't see anybody in a position where they need to drop, but just for all kinds of legal reasons, you got to have a firm grade by the drop date. So I'm giving you this introduction. The problem assignments are there. And I kind of recommend that if you do spend some time, you just take a look at the problems, do the easy ones. Okay. Now, if you want to really get ahead, let us slack off the week you get back. You can do them all. It's all up to you. Problem assignments are there. Okay. And much of the problem assignment, each problem assignment is fairly easy. If you have the basic ideas. Like you can always now calculate a directional derivative. So the problem says calculate this directional derivative for this function at this point in this direction. That ought to be like falling off the law. Okay. If it says this level surface here corresponds to this temperature function, now find the total temperature flux through this level surface. Well, it's not going to ask you that. But if it asks you a question like that, you know, that's when you just said, let's get some more explanation to make sure that we have what we need in order to do this. Okay. There's also some stuff in there about implicit differentiation. And I'm just going to give you a quick blurb on that, because the basic operation is pretty simple. Get a board clean, but it's got to use up more. There you go. Got to get the cloth dirty or they don't look like water. But the cloth can always be. Okay. Let's say you got it. Okay. This implicitly, well, there's a set of points X, Y that satisfy this function. Okay. And let's say that this function, plus 12 equals 0. This then gives you a curve. Might be a pretty complicated curve. Okay, we don't even want to try to draw it. But I'm going to put a different number here in a minute. Okay. What is dy dx at the 0.12? If I did my arithmetic correctly, yeah, I'm pretty sure I did. Then 1, 2 is a point on this curve. Okay. Well, Back forward to what I'm doing here. Wait a minute. Yeah, I don't want to do that right now because I'm confusing myself. And I'm just gonna pretend I didn't start that. Okay. There's a geometric connection that I was thinking in terms of. And because of limited time, I'm gonna leave that. There's a whole thing on implicit differentiation. And it comes down to like df dy over df dx equals dx dy. Or df dx over df dy equals dy dx. Okay. And I wrote that down wrong twice, so I gave up. I just need to give myself a little more time to think. So we'll talk next time. It'll be in the problem assignments. You can read examples. It's not that hard. But into it in more detail when we get back. Okay, I want to talk about just the feel of the chain rule. And I'm trying to get the camera to focus. Okay. Here's the check. Oh. There's a common way of writing the chain rule. Okay. What does this say? This says that this is the rate at which U changes. I'll say it a little different. Say a change in X drives a change in U. Okay. You tell me how much X changes. If I got the information on the function, I can then tell you the rate at which U is changing. Okay. I'm going to say this is the rate at which a change in U drives a change in Y. This is the rate at which it's a change in X drives the change in Y. So what we're saying with the chain rule is, for example, if 1 unit of change in X causes 3 units of change in U, and 1 unit of change in U causes 4 units of change in Y, then 1 unit of change in X will cause 3 units of change in U, Each of those units of change in U will drive 4 units of change in Y. So 1 unit of change in X drives 4 times 3, 12 units of change in Y. Now, does that make any sense? That's a thing you should probably want, maybe think about pondering a little bit. I'm going to use that idea. So let's say we got a function f of x, y. X is a function of t and y is a function of t. What happens if t changes by 1 unit? Well, maybe we're given t, then x changes by 2 units and y changes by 3 units. In other words, I'm saying that the derivative of x with respect to t is 2, derivative of y with respect to t is 3. That means x is changing by twice as many units as t does, y is changing by 3 times as many. What change do you get in change in t drives a change in x and a change in y? Now, the change in x will drive a change in f and a change in y. Drives change in f. In the sense that f is fx dx plus fy dy, as we saw much earlier. Okay, that's your differential. Okay, which you encountered in section 3. Yeah. That's what we began talking about. Okay. Then it makes sense that df dt equal fx times dx dt plus fy times dy dt. This is the rate at which x changes with respect to t. This is the rate at which f changes with respect to x. In other words, this is the rate at which a change in t drives the change in x. And this is the rate at which the change in x derives the change in f. It's just a chain rule. It looks a little more like the chain rule if you write this instead of fx, okay? Write it as df dx, and there's your chain. You know, if you think of canceling the x's, you got a df dt, right? Well, that's the df dt that you get due to the effect of t on the x variable, but f is a function of two variables. And just like a change in y causes a change in f, a change in x causes a change in f. You add those two changes to get the total change. Comes right back full circle to what we started with. So I complete this by saying plus your change in f due to the change in y that depends on the change in t. Okay? Now, if you understand that, let's say you have a function okay, g is a function of x and y, but x is a function of two variables, u and v, and so is y. Okay? Then partial of g with respect to u is equal to, and you know, when I did df, dx, those should have been partial derivatives. Now the dx, dt, and dy, dt are okay. They're just plain old derivatives because x is only a function of t and y is only a function of t. Okay, x and y are functions of one variable, so we just have the dx, dt. Then we have the partial of f with respect to x and y. Okay, so just correcting the notation there. Partial of g with respect to u then. Well, what causes g to change? Well, if x changes, g changes, right? So you have to account of how much g changes with respect to x. Okay? But then x changes with respect to u. Okay? So you have to multiply that by the partial of f with respect to u. U changes a little bit, so g changes. Why does g change? Well, part of it is that g changes with respect to x changes with respect to u. So whatever that change in u is, determines the change in x. And then you multiply that by the rate at which g changes with respect to x to get the rate at which g changes with respect to u. Okay? But of course, g also changes with respect to y. And y changes with respect to u. Okay? So a change in u causes x to change, which contributes to the change in g. A change in u causes y to change, which contributes to more change in g. And then, of course, by analogy, with exactly the same reasoning, partial g with respect to g, v is partial of g with respect to x times a partial of x with respect to B. And then G changes because Y changes. And Y changes as a result of a change in V. Now, if you follow this reasoning, it's easy to extend it to any number of variables on G and any number of variables on each of the variables that determine G. Okay? Your book does the tree diagrams. Those tree diagrams ought to be pretty self-explanatory. I'd never seen them before I looked at this book, I don't think. But they're, it's pretty obvious how this can be done in a tree diagram. Since I've only got 4 minutes left, I'm not going to do that. Because I do need to, first of all, figure out where the doctor's office is. I know where it was. And it's in the same general area. I need to leave myself a little bit of room. Because I've never been able to get there at a time when everything's open. So I need a couple of minutes. Take me 10 minutes to get there, 10 minutes. So that's just kind of an introduction. Chain rules and directional derivatives, which are the next two sections we're going to be working on. And I do recommend you scan through those sections, look at a couple of examples, look at the problems, and think about how all this applies at the very least. That would be your assignment for the remainder of this week and for the beginning of next week. No assignment for the Saturday through Sunday, which is your effective spring break. Okay. And that way we'll be able to kind of quickly wrap up chapter 4 and start moving into integration and dimensions. Okay, we're really, because of the snow delays, we remain pressed for time. Basically, I've got to cover 3 sections a week for the rest of the term, and we'll just barely get there. Okay.